Okay, so we're gonna look at one, hopefully one last thing with electric fields, and if we were in regular classes in my lab, we'd be playing with one of these for sure. But we'll do what we can. This, of course, is a Van de Graff generator, which most people know, shocks people and that type of stuff. And it's lots of fun. We played with it in grade 9 science when we do statics and that type of stuff. But this is just a basic laboratory one, very similar to the one I have in my lab. And of course, most people know, you get the thing going. There's a belt that just rolls up and down here. So there's goes up and down. There's two pulleys on either end, and basically it just builds up static electricity. So really, what ends up happening is this part up here literally becomes like a giant Q. That's literally what it is a giant charge, and gives off a massive electric field. So there's a huge electric field as well as supplies electric potential. And electric potential is actually the key for these things because they use high voltage. And if we go back to Gauss's laws and stuff, this is a metal conductor. And when you build up the charge, all those little charges, like we talked before, all those little tiny charges will reside on the outside. We'll just say it's positively charged. Becomes positively charged all over the place, and that charge will actually reside on the outside of on the outer part of the metal sphere. So actually inside of it would actually be like the safest place to be, because with Gauss's law, the electric field and everything inside would actually be zero. But that thing builds up a huge charge, and as that builds up a huge charge, you can go to the kq over r squared. It builds up a huge electric field. But more importantly, it builds up a huge electric potential, which is the kq over r. And the great thing about it is the higher the voltage, the bigger the shocks can be. And of course, the class thing is, somebody comes along and they touch it, whatever, you get close to it, you get the little zappy, 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 zap. And of course, the whole thing is, their hair stands up and all that kind of stuff. All the classic type things. Well, the more potential you have, the higher the voltage, the more of an effect you can actually get. So when you have stuff like this, there's different sizes, but the bigger the sphere is, the more charge it can hold. The more charge it can hold, more Q value. Okay, so you got more charge out of it. So you have more charge, and because you have more charge, you can create a higher voltage. And the higher the voltage, you get a larger electric potential, which then allows you to have more of a potential difference. So the higher the voltage, the higher the Q, the bigger difference in potential it can actually jump, and it can actually jump farther. So a low voltage one might be able to zap that far, okay, but a higher potential one will zap that far because it's got more potential. It can do more of a potential difference. And that's sort of how the voltage stuff that you guys are working on kicks into one of these things. And one of the cool things that you can do with this, and again, if we were in my lab, we'd be doing this, but we're not in my lab, is one of the classic tricks is to, let's get rid of this stuff a little bit, clean that up. One of the classic tricks is to take the gas discharge tubes that you guys played with in grade 9, these guys right here, you put electricity through them, they glow different colors. Well, you take one of these tubes, and if you put it like this beside the Van de Graff, you don't have to hook it up to anything. If you just hold it beside the Van de Graff like that, it won't do anything. Okay, now the reason it won't do anything is because this end over here, oops, wrong tool. This end here and this end here, they are at the exact same radius from the actual Q. So the electric potential here and the electric potential here are the same. So for the charges here, their potential energy here and here, the potential energies of the charges are the same at those two locations. Since those two potential energies are the same, there's no reason for the charges to move across, which would cause it to actually glow. So this, when it's set up like this, it'll do absolutely nothing. Now let's just move that out of the way. Whoops, wrong tool. Let's move this out of the way and move it over here. So same thing over there, will do nothing. But If you take the exact same tube and you do something like this, it will glow like crazy. Let's get some glow in here. This thing is going to glow like crazy inside. And the reason it glows inside is this end and this end are a different radii from the Q source. So the potential energy here and the potential energy here, those two potential energies are not the same. So since the potential energies are not the same, charges will go from one end to the other because they can change their energy. Now we've talked about this before. It's all about changing energy. They can't change their energy by moving from here to here. There's no change in energy, so there's no reason for them to go. Between these two, they can change their energy. So since they can change their energy, they will move from one side to the other, which then causes the gas inside to glow a nice color. And then there's a purplish color, I think it's like potassium or something like that. It'll give a nice little glowing effect. And that's the basic idea behind how these Van de Graffs work. And again, the higher the voltage for these things, the closer or the farther away you can go and still get shocked. So you're out here, okay, you might not get shocked by this thing because the voltage isn't high enough. Maybe the electric potential is only enough to go over here. Well, crank up the charge, crank it up by hopefully having a bigger sphere, and you can go even farther and then give you a nice little shock, which is always lots of fun. Okay, so that's the idea behind a Van de Graff generator, and that's how it kicks into what you guys have been doing. You can look at the electric fields, although we typically don't use these things to apply forces really. There's lots of tricks with pie plates and stuff that to get pie plates to fly around, that type of stuff, but it's more about electric potential, whether it's these things or those little lightning ball type things as well. It's about electric potential, having a high potential area and a lower potential area somewhere else, and trying to get the charges to jump from one potential to another potential. In fact, this is also, like it's an analogy sometimes even for an atom and stuff that, where this could be the nucleus, and these ends are like electron orbits and stuff that. It all sort of kicks into the same type of thing. Okay, like this could be one electron orbit, this could be another electron orbit over there, and they jump around and with different energies, and of course when they crash back down they give off light colors. It's all the same type of idea, all the same type of thing, connecting some of the things you guys took in grade 9 to what you guys have taken in chemistry, as well as a little bit in grade 12 as well. So they're great little gadgets and toys for working with electric potential and shocking people. Just lots of little fun tricks. Unfortunately, we're not in my lab, otherwise we could do a whole bunch of these things. I could show you some other stuff, but that's sort of what these things sort of are all about.